Okay, we're going to look into the conjugate root theorem, but I'll start by saying if we had a function, this one here, okay, 2z cubed plus 9z squared plus 8z take 39, or any function where the coefficients of each of these terms did not have any imaginary components. If that's the case, then there's two situations that apply. There could be that all of the roots for the solution are all real numbers, or if we did have one that was an imaginary number, then it would have to have its conjugate pair as a root as well. Otherwise, when we multiplied them together, we wouldn't have these real terms. So what I'm going to show first is just that if we have z1 is equal to a plus bi, where we have an imaginary number, okay, that if this is a root, then the other root for a situation where all the coefficients of the polynomial are real numbers, then this, if this is a root, then this must be the other root as well. Okay, the conjugate pair must be the other root. All right? Otherwise, we wouldn't end up with all real coefficients in that polynomial. Okay, so I'll just show that this works. So if we had some z value, take away this root here, 8 plus bi, brackets, and then the other factor that I had was z take away a take bi. Okay, I'm going to expand out this -1 to each one of these. Okay, and I'll end up with z take away a, take away bi, and I'll have z take away a plus bi. I'm just going to pair these up so it's more obvious. So if I have z take a plus bi, and if I have z take a take bi, this is the difference of two squares. So I can say this is equal to z take a squared take away bi in brackets squared. Right. If I expand out these brackets, z take a squared, I'll end up with z squared take away 2az plus a squared. And if I square this, I squared gives me -1, so I'll end up with a positive there, and I'll just have plus b squared. Now, if you look at this expression, this polynomial, all of the coefficients of z, and even the constants, they have no imaginary values. Okay, so I've just shown that if you multiply a complex number with an imaginary component by its conjugate, okay, then you'll end up with this situation where there are no imaginary components. So, if we look at this question, which you've got here, it has no imaginary components as coefficients or even as a constant. Okay? So if we know, or we've been told, that one of the roots is a complex number with an imaginary component, then we know that its conjugate must be the other root as well. Okay? So I can then say that, therefore, -3 take away, okay, take away 2i, better cross this out, -3 take away 2i is a root as well. Okay, so now that I've got the two roots, -3 plus 2i and -3 take 2i, I know there's going to be another root because this is z cubed. Okay, and because these two are imaginary, I would expect the other one to be just a purely real root. Okay, so if it's not, then I'd be looking at my working and checking it all again, because there's got to be a problem there. Now, if I was to write this out, I could say that 2z cubed plus 9z squared plus 8z take 39 is going to be equal to z take away this first root, so take away -3 plus 2i, multiplied by z take away the second root, so -3 take 2i, and then that is going to be multiplied by some az plus b value. Okay, this is my last unknown root that I'm unsure of, I don't know about. Okay, I better put my brackets in here and here as well. Okay, so from this, if I multiply z by az, it has to equal 2z cubed. So therefore, my a value is equal to 2. Now let's sort out this b value. It's going to be this here multiplied by that multiplied by b. Okay, because it has no z's associated with it. So this is the only constant term that has no z's with it. So it must be negative 3 plus 2i multiplied by negative 3 take 2i multiplied by b is equal to negative 39. Okay? Now from here, this here is the difference of two squares again. All right? Negative 3, so it's going to be negative 3 squared take away 2i squared. All in brackets, times by b equals negative 39. Now negative 3 squared is 9, and if I take away I squared times by 2, it's the same as saying 9 plus 4. Because 2i squared will give me 4i squared, and I squared is just negative 1, so we end up with a positive there. So 9 plus 4b is equal to negative 39. Okay, continue on from here. It's just going to be 13b is equal to negative 39, and I divide both sides by 13, and I'll end up with negative 3. So I've got my a value, I've got my b value, so I know that the linear factor, one of the linear factors, is equal to a, which I worked out to be 2, multiplied by z, 2z, like we've got up here, plus the b value, so plus or take away 3 we've got in this situation. So that's the other linear factor that we worked out. Now, I didn't want the linear factor, I wanted the roots. Okay, I've got 2 of them already, I need the other one. Now we know the roots occur when this is equal to 0. Okay, so if I add 3 to both sides, I'll end up with 3 is equal to 2z. Divide both sides by 2, I reckon I end up with z is equal to 3 over 2, or 1.5. Okay. So, my 3 roots. Are negative 3 plus 2i, negative 3 take 2i, and the last one is 3 on 2, or 1.5. And again, it checks out. This was a real number. We expect it to be a real number. Because if it was an imaginary, then we would have ended up multiplying this out, and our original values here, the coefficients, would have had an imaginary component in them. So this all checks out. All right, thanks guys.